get rid of me, so we can see what's going on. So this is LTSpice. This is the screen that you'll get up when you open LTSpice. Hopefully the first time if it all works properly. And what we need to do to start with is open up a new schematic. So let's just click on there. So now we've got a new schematic, and that means that we can actually start to put components and things on this blank piece of paper, really. And the only problem I've got now is that I can't see the circuit I was supposed to be designing, but I'm sure we can come up with something. So to get hold of our components, we can use a lot of these things up here, and the one that's usually of interest is this one here that allows us to pull up components, lots of them, and then there's a few that have been brought out specially that we commonly use, like a resistor and a capacitor and inductor. There's a lot of other stuff up here, but we don't need to worry about that particularly at the moment. So if we go here, it brings up a sort of a library, and there are lots of libraries which you can get to by doing all kinds of other things, but you can see there's all the general components in here that we need. And part of the skill, if you like, of LTSpice is understanding what's available and where to find it. It's all there somewhere, and there's lots of stuff on the web. If you haven't got a component, you can download it, and that's the advantage of it, because you can go to any of the major semiconductor companies and download models for quite a few of their chips, and they should then perform pretty close to the real device. So in this case, we could put down a transistor. Let's put down a transistor. So we just drop our transistor, and then we can pull up all kinds of parameters about the transistor just by clicking on it, and we can have this pick new transistor. So if we ever knew what transistors were and we had a particular one, we could go and we could select any of these transistors if we were interested in. It tells us a little bit about them, but this is the part number you'd buy from transistor company or Farnell or RS or somewhere. And you just click on that and OK, and then that has the model for that particular transistor, so you can design circuits with that in mind. To get rid of it, we can use the cut, and just gets rid of it like that. So we go back to our component. What we want for our circuit is a voltage source, at least one anyway. And so we have one over here. We had another one in our circuit, didn't we? We can rotate this with a Control R, get the positive in the right place. So that's probably good enough. We can always move it if we have to afterwards. And then we can pick up some resistors. And so I get the numbers all wrong on the resistors, but again we can change those if we have to. Right, so I think they're the major parts of our circuit. Got a bit of paper down here, let's have a look. Okay, so they're all right. So that's our sort of basic structure. We can then pick this one up, which is a wire, and that allows us to then click on the blue blobs and make things connected. You can see this is much quicker than building a real circuit. Okay, so that's all wired up. We need to obviously give some values to the components. So we just go to the thing that we want to change, and we right click on it, and then we can just type in the box. This one was a 2 ohm resistor. This one I think was a 6 ohm resistor. This one was a 4. We can obviously make them what we like, but we just like them to line up with what we had before. No, not that one. And that one was a 2. Okay, so that's given values to our components. We now need to do the same thing for our voltage source. That one had a 4 volt source, and this one was a 2 volt source. Okay, so that is our circuit constructed. Now we can start to think about analysing it. And the only sensible analysis we can do on this one is to do what our matrix analysis was doing, to work out the various currents and voltages that flow through this this system. So we need to tell the system now to do a simulation. So we can go up here to our simulate command, and we can do edit simulation command, and it gives us a choice of simulations that we can do, only one at a time, unfortunately. And I'll probably do another demonstration in a minute. It demonstrates some of these other features which are quite useful. Some of them are more useful than others. Obviously it depends what sort of answers you want to know. So we'll look at these other ones in a bit, but the one we're interested in is this thing called as a DC operating point. And helpfully it tells us compute the DC operating point, treating capacitances as open circuits and inductances as short circuits. So this is DC analysis. This is what happens under static conditions, which is sort of what we want for biased conditions and what we want to solve these simple equations here. And it helps us by telling us that we can have, this is the syntax, .op, anything with a dot in front of it is called a spice command. So that's, the computer knows that's a command it's supposed to do something with. So there's no options here, we just have to do an operating point analysis. And then LTSpice is unusual in some ways, is it allows us to then drop the command on the text. And in fact you can drop all kinds of commands on the text, and if you want to change the models of these devices, or the transistors in particular, you can just type the new model in as text on the diagram, or cut and paste it, and it just uses it in the transistor. So it's quite helpful from that viewpoint. So now this is going to all set up to do an operating point analysis, and now all we need to do is simulate it. However, there's one thing missing at the moment, but what I will do is I will run this without that thing in there. Yeah, you're jumping the gun. I'm just telling you that it won't run because there's going to be an error, and you're stealing my thunder, Daniel. So if I run that, yeah, right. So I run that, and it should tell me, as Dan says, that it doesn't have a conduction path to ground. Let's see. Circuit does not have a conduction path to ground. Please flag a node as ground. Okay, and this comes down to the fact that voltages are relative, and at the moment there's no absolute voltage in here. All we know is that this, for example, this one is 4 volts different from each end, but we don't have any absolute measurement for it to say that's 0. So what we do is we pick up this thing, which is called a ground, and we can attach that to any node in the circuit, and that becomes our equivalent of 0, an absolute 0, not a relative 0. So we just drop that down. Yeah. This button's useful. This zoom to full extent brings it all back again. Put a wire on that. You can drop it straight on to a node if you want to, but I prefer to have wires because then you don't get things that you think are connected but actually aren't. And now if you run that by hitting the running man, that hopefully should run okay this time. Okay, so what that's done is it's done the analysis that we did by hand last week and helpfully linked everything together. So now we can see that voltage at a certain node, and it's just numbered the nodes internally, are whatever it is it's calculating them at, and the currents through the elements. So current through R4, R3, R2, R1, V2, and the current through V2 and V1 are all listed here. And that's really good because it tells you what's going on. The only downside of this is because it doesn't label the nodes visually, it's a bit uncertain as to actually which way is up in many ways. So we can see that this is going to be node 1 because there's obviously 2 volts across it, and whatever. So we need a way then of working out where the nodes are. And what we do is we get that just by putting the cursor on the thing, and if you see at the bottom, I can't move my mouse because it'll go away, but if you look at the bottom line above the sort of Windows bar, it will say this is node N001, and it also then tells you the operating point, VN001 equals 2 volts. So we can go and just point at different parts of this circuit. So this one here, we can see the current is minus 142.8 milliamps. Again, it doesn't tell us which way is the positive direction, and that's the slightly annoying thing about it. What we have to do is know that current flows from high voltages to low voltages, so we have to look at the voltages at either end. That's 2 volts, and that's 1.7 volts, to know the direction of positive current. So it's going to flow, in this case, from left to right. So so there's a little bit of uncertainty as to directions, but you have to just apply a little bit of common sense to it. And likewise, we can point all these things. This one will tell us the current going through it, and also look, it tells us the dissipation in terms of power dissipation as well, and also dissipates what's being dissipated in these resistors, so you can see what's going on. And that is quite a simple way of analysing what's going on, which is very helpful, I think. Hopefully Dan got the same answer as me, if he's following through on it. Yes, I did. Good. So that's all right. So you should get the same answers, because all it's doing is solving the equations for these meshes. It doesn't really understand that these are components. It just sees them as models. So that's a useful thing. We can go a little bit further. Let's do another one. So we start a new schematic, and let's look at the transistor equation that we had before. Component. Right, so we're going to need a voltage source. We'll have one of those. We'll pick up a transistor, just a basic transistor. Put that there. Pick up a resistor for our base. Put another one up here, and I think that's probably about all we're going to need. We're going to need another voltage source. Right. So put that one over there. So we can pick up a voltage source, and we're going to use it as our power supply. If we want to emphasize that it's a power supply, and just for neatness of diagrams, we can actually go to a different library. It takes a bit of digging around normally to find it. So these are all the libraries we can get. So I think if we go to MISC for miscellaneous, it picks up all kinds of other things, and we can pick up things like battery or cell, which is half a sort of a battery, if we want to have different symbols. And you can start to see that there are all kinds of other strange components and things in here as well. So let's do this. Let's put up a battery in there instead of our. In fact, while we're about it, if we then go back to a different library, we can then pick up things like, let's say, op amps. And just to show you, so this comes with linears and analog devices, library of all parts. These are all different types of op amp, and we do op amps after Easter. But there are lots of them, as you can see, loads and loads and loads and loads. And other companies have loads and loads and loads as well. And we will start looking at what op amp is and what the differences between all these things are. But if there's one particular one you want to use, this allows you to then, this was CMOS op amp, whatever, they all have the same kind of symbols, but they're all different. This one's a low noise precision rail to rail output JFET single, well, it comes in a pack of 4 sometimes, but they all have slightly different internal performance. So you can model your circuits with particular brands of op amp to see if they will behave differently. Okay, but we don't want an op amp, so we get around that. Right, so now once again we have to wire this up, and once you start messing around with slightly more complicated circuits, there's a lot of scope for it going wrong very easily, as I'm sure we're going to find out. So one of the other things we can do is we can just put a wire on here. So we've just got a bit of wire on that point, and we can do the same kind of thing. So for more complicated circuits, we might want to just not join things up particularly. So what we can do is then label it with this one. So we can pick a label, and let's call it VCC, just convenience, and then we can attach that to there, and then we can attach that to there. And now, even though there isn't a wire joining those two, because they're labelled the same, that makes it an implicit connection. so it just makes diagrams much easier to declutter. We could have done the same thing down here we can put more grounds on if we want to. In fact, we'll do that. So we need a ground, we know that. Pull our ground, attach that there. We also need to ground this part of the circuit as well. Oops, there we go. Just put that there. We draw that. So now we can just check. We've got our battery, it's connected implicitly there, so we've got a power supply in. We've grounded it, so the computer knows where everything's going on. We've got our resistor for our load. We've got our resistor for driving our base current in, and we've got a voltage supply here and one over here as well. Now we haven't put any component values on this at the moment, so let's change this. And the nice thing is once you've got this, you can mess around with it. So put 5 volts on there. We'll worry about that one in a minute. So this one, let's say it's 2K. That seems like a sensible number. So it understands K. We can put that in there. And this one, we'll make that one. Let's start with 47K. See what happens. Okay, so just for the sake of argument, we'll just call this 0 at the moment, otherwise it's going to throw some kind of error up. So at the moment we've just got a circuit here, we've got nothing in, we'd expect to get nothing out. So we can do an operating point analysis on this if we wanted to. But what I want to do is show you how to get the transfer function, if I can remember how to do that. So this is where it's a bit suck and see what happens. Let's put a simulation command on it. So this time we're going to do a DC sweep, and this allows us to change a source from one value to another value and run the simulation and get an operating point effectively, and then we just keep changing that to get lots and lots of different operating points and join them together, and that should give us a transfer function. So if we change V1, which is this source over here, which is our input, and we type a sweep, well there's all kinds of things. Well, we'll go for a linear sweep, which is straightforward. Our start value can be 0. Our stop value, well it's never going to get higher than 5 because that's our power supply voltage, so we'll call that 5. We won't bother about increment because we'll just let that decide for itself how that's going to do it. So, and again it drops it on so we can see what we're going to do. So this is a DC sweep, changing V1 from 0 to 5, and with any luck, if I run that, we won't get an error, but I always do the first time, so let's just see what happens. Actually, the other thing we could do, the nice thing, would be to put our output on here so we know what we're looking for. We haven't got to worry about nodes at that point. So we'll label that V out. So now we've labelled that, that should be easier to find in our big pile of results that will hopefully come out of this. Okay, let's close that one down. And now it says I've done it, so something's happened, which is good. What I might want to do is look at the output voltage, and that's looking at what happens when we've changed this input here from 0 to 5 volts in steps. What is this voltage for every possible value of input here? What will we get at the output here, which is our transfer function? And it's given us this response here, so we can make that big and have a look at it. And so this is replicating the transfer function that we got when we analysed the common emitter amplifier. So you can see that for small voltages going in, 0 volts going in, we get 5 volts out, and that's because there was no current flowing through, transistor's off. As we then increase the voltage, we get to the point where it does this transition, which we noted was exponential, and then gets to the point where it's effectively saturated and can't go any further, which is close to 0 but not exactly 0, and then we don't get any more life out of it at all. So this is the only interesting bit of the transistor, where the input varies between, or whatever that value is there, and that value is there. Now if we want to know what this value is here, and this value is here, we can just right click on this here, and we can attach cursor. And this allows us, we can then pick that up, drag it with the mouse, and you can see that it allows us to look at any point on this curve and see what's going on. And the box in the corner down here gives us a readout. So horizontally it's saying this is 792 millivolts and vertically it's 4.7. So we can pick off any sort of point on here. Right, so now we can sort of start to look at our circuit and say, well, how do we work out what's going on in this circuit? We understand that we would like to be operating maybe at this point here at 2.5 volts. As a bias condition with no signal going in, we'd like to be sitting at this point here, so that then when an input signal comes in, it moves around this point and gets amplified and comes out of here. And the simulator will allow us to dig into that a little bit more as well. But we also know that this is the true transfer function, so it's an approximation, well, so our simplified model is an approximation to that straight line that we developed. But we'd like to know the slope of this at this point, because this will tell us the gain straight away. So we just need to work out what the slope is at any given point here. And again, this is a useful thing to want to do. Again, we can add some cursors. If we add a second cursor, so we've got two cursors on here, what we can now do is move that over here, drop it on there, and now this cursor box now has both cursors on it, cursor 1 and cursor 2, but also helpfully gives us the difference between cursor 2 and cursor 1. So it tells us the difference horizontally and difference vertically, and then it goes a step further and tells us what the slope is. And the slope is the gain of this amplifier. So at the moment, looking at that bit, the average slope between there is 4.09. So we've got a gain of 4 we would expect to get off this amplifier, roughly. Now, if we biased it at a different point, the slope at that point there is 3.14. So you can see that if we biased at this point here, not only would we not be able to move very far in terms of our output, but also we've changed our gain. So you can see that the slope, if we take the average slope, we're back at 3.87, but it depends how accurate we want to be, but that's the average. We bring it back down, just look at that little bit there, the slope there is 4.1. So it's nearly constant, but is it constant enough? It depends on your application as to whether you think that's the case or not. What you can do is you can get close to see what's going on, and then you can actually just zoom in on an area to see how good or how close you really are to it, and see what the real gain is if you wanted to on there. Okay, so we've just zoomed in on that bit. So it's quite flexible. Once you know what you're doing, it's very helpful to allow you to get to where you're going with that. Okay. Right, so there's our circuit. It's all good. What we can maybe now do is start to set it up as if it was in the bias conditions. Let's go back here. So we want 2.5 volts here. We can read off what we need at the bottom. 1.35. So we want an input voltage of 1.35 volts to put us at this position here with 2.5 volts at the output. So maybe we can check that out. We can just set that input voltage to be 1.35 volts. And if we then did an operating point analysis, if everything is all well and we've got a good understanding of what's going on, which is, to be fair, is not guaranteed at this time in the morning, we would expect this to be about 2.5 volts out. So if we go back to our simulate command, edit that, and we go to operating point. Unfortunately, LTSpice is not that great at. It used to do this really well, so you've got to take all that nonsense off the end to give us our .op. It semicolons that one out of the way, and so it's now going to do an operating point analysis with any luck. And fortunately for us, V out has come out at 2.5713, so we're not far away from our initial analysis of what was going on. So you can sort of see how all these things start to line up, which is quite nice as well. The other thing we can do, and let's hope we can do it as well, is we can work out what the gain is with frequency. So this is just another one of the analysis, and we'll just see if this one actually works or not. We're expecting this gain to be about 4 or so, roughly. We'd like to see how that might change with frequency if we put a frequency in here, so we can do a small signal analysis in this over frequency. Right, so let's just see if I can remember how to do that. Edit simulation command. We want to do AC analysis, and this completes the small signal AC behavior of the circuit. I remember we haven't done that quite yet, I don't think. We'll do an octave sweep. We'll put 100 points per octave. We'll start at 1 Hertz and we'll go to 10 kilohertz just to see what happens. Right, and we'll just run that and see what happens. Oh no, because what I've got to do, yes, that's right. So I've got to go in here and I've got to set this up for an AC. So this is just telling it that I want to do a small signal AC analysis. Doesn't really have any bearing, but it's going to put in the equivalent of a 1 volt signal for its AC signal, and see what goes on. Okay, and again we can just select any variable off here to plot. We're interested in V out, and V out we get a straight line, which is actually a good thing in this respect. And it's difficult to read down here, but we've got a number. Let's get rid of this. Is the phase response. We don't need that. So we've got this value of 12 dBs or so of gain, and this axis is frequency. So if we put a 1 Hertz signal in, we would get a gain of 12 dBs. If we put 100 Hertz in, we'd get 12 dBs, and if we put 10 kilohertz in, we get 12 dBs. And this is all ideal stuff, so this is actually the ideal response. So simulator's given us the ideal response. If we don't like dBs, we can plot it linearly. And look, our gain is 4, and this scale is very tight, so we've got a very good 4.07 whatever gain across the whole frequency range for this amplifier. So that's pretty good, isn't it? Get a good analysis of what's going on. The other thing we can do is just check what happens. So this source, this voltage source here, has a great deal of flexibility in terms of the circuit. It can represent all kinds of things. At the moment we've just got it as a DC source. It's providing our 1.35 volts of bias, which puts this halfway up its operating characteristic, as we've now seen. So this is now biased. What we're not doing is putting any kind of AC signal in. This AC analysis we've just done said if you did put a signal in, you would get a gain of 4 out. So let's do something. Let's change this into a sine wave source. We're allowed to put a DC offset on. We need that at the moment for our bias. And then we're going to put in an AC signal. So let's put in an AC signal that's amplitude is what should we say, 100 millivolts, and let's give it a frequency of 1 kilohertz, and these other things we're not interested in those. So that just gives us a sine wave output. Okay, so the amplitude 100 millivolts, 1k. So 100 millivolts, we'd expect to get something like 400 millivolts out of this thing if it ran properly. So now we go back to our simulate command, and what we're now going to do is something called a transient. So this is a nonlinear time domain simulation. So this is going to give us the response of this over time. So we put a sine wave in, we should expect to see a sine wave coming out. So we've got to tell it how much time to simulate over. So let's give it 0.1 of a second. Let's see what happens. Time to start taking it. Ignore that. Ignore that. And that's the basic analysis, and that should do okay. So that's a transient response for 0.1 of a second. I think that's all right. It will soon tell us if it's not. Okay, and so now we can look at V out, because that's what it's defaulted to, and we're getting a sine wave out. And we can start to look at the numbers to see whether or not it's what we expect it to be. What we can also do is just click on here to see what the input was. And you can now see, if I make that big, that we've got a small input centered around 1.36 volts, and we've got a much bigger output centered around roughly, well, 2.5-ish, which is what we sort of expected. And again, we can zoom in on a bit of this just to be interesting, and we can see yeah, we've got a sine wave. And what we can also see is that they're in opposite phase, which is what we expected from the common emitter amplifier. As this one's going up, this one's coming down. And we've got a gain, and if you measured it, and you can measure it with the cursors, you'll find that you're getting what you'd expect to be. So again, we can add the cursors to this, position that at the peak, position this at the peak, and then we can read off down here what's going on in terms of frequency. Is the phase shift caused by delay? No, the phase shift is caused by the fact that the gain is negative. It's got an inversion in the gain. So it's a gain of -4. Remember, the slope was negative, so it went down. So that's what's causing the inversion. Okay, so so if you get the difference between them, you can see that we've got 806 millivolts or so peak to peak, and we put in 100 millivolts peak, so that's 200 millivolts peak to peak, and divide one by the other, you get 4 roughly. So this allows you to see the effect of what's going on, and then you can start to investigate the circuit. Let's say we put in a bigger signal. Let's put in 1 volt. And again, we have to run it with the running man. And looks like it's bigger and whatever. Let's zoom in a bit and see what's going on. Now we're starting to get something that doesn't look like a sine wave. Yeah, the input is still a sine wave and it's small, but the output is saying, well, actually, look, I've hit 5 volts here. I'm very close to 5 volts, and that's my power supply. So I'm trying to go higher than power supply, so I'm clipping. That's what's called. And likewise, the other way, I've gone down and I've hit 0. So we're trying to cover the whole of the transfer characteristic with our input signal, and it's starting to get distorted. And what we should see is if we just reduce this that's the current. If we're interested in the current, delete this trace. If we then go back to this and change the size of the input signal again, and let's go a little bit smaller. Let's go down to let's try 0.5 volt. See what happens with that. Okay, so it's looking like it's in the range of the power supply at least. And it's looking a bit like a sine wave, but actually you can see that this bit here is sort of narrower than this bit here. So we're starting to see distortion. We're starting to see different amounts of gain at different levels of signal as we move up and down that transfer characteristic. So we're getting lower gain at the top end and higher gain at the bottom end. Likewise, let's just pick again. We just go a bit bigger. Let's see. Because if I'd stimulated over a short period of time, I wouldn't have to keep doing this. It's just starting to get too far, really. But you get this sort of general idea that you can start to investigate what's going on. Of course, if you put a really big signal in, let's put in 5 volts. So big amplitude going into this thing now. It's starting to get a bit weird, and we're starting to get an approximation almost of a square wave. These steppy bits are due to the solution only being solved at certain points. We can solve that if we're interested by specifying a maximum time step. So this makes it do more calculations, and again you just have to sort of guess what we want in there, but it says that it's going to do it every whatever fraction of a second that will be as a minimum. So it should take it longer if I've got the numbers right, but hopefully it didn't take it much longer, did it? So I need to go a bit further on that. Put another couple of noughts on. That's taking longer, I think, isn't it? In fact, we've crashed. Does that on my computer sometimes? Oh no, there we go. We're sorted. Right. See, it's taking a lot longer because it's doing a lot more calculations, and you wouldn't want to be doing those by hand, Gaussian elimination. And you can see that when you fill in the gaps, you're getting a much squarer waveform on here. So you trade detail of analysis for speed of calculation, and this is quite a simple thing to analyze. If you're analyzing something that's really complicated, there's a bit of an art to making sure that you get the right amount of calculation against the right amount of time to sort these things out. Okay, so I think that's a good simulation of what's going on, and that allows us, or allows you at least, to have a play and build some circuits and have an idea of what's going on when we do simulation, and hopefully that's made it a little bit clearer what's going on. What it means is that any examples that we now do, you should really be able to put into simulation and check them out for yourselves.